Welcome into learning the third unit we're going to be learning this year. Chapter 3 is going to be about functions and polynomials. And it's alright if you don't know what I'm talking about yet, because that's exactly what you're going to learn today. So, in this first lesson, we're going to be having an intro to polynomials, which would be understanding variables. We're going to be able to express expressions, patterns, and rules in situations with variables. Variables are symbols that can change on their value. So let's get started. So let's take a look at our learning goals for today. Our first one is to understand the meaning of using letters. And from now on, I'm going to read it as variables. So our first one is going to be understand the meaning of using variables to express numbers. Variables can be used to express previously learned arithmetic and calculation formulas. Variables can be used to express quantitative relationships and changing laws in some simple problems. So that's the course outline. And now, let's get started with our lesson. So we start off with contextual introduction. As you can see, there's this little frog right here, and we're going to make some observations on him. So our observations are, if we have one frog, we're going to have one mouth, 2 eyes, and 4 legs. 2 frogs gives us 2 mouths, 4 eyes, and 8 legs. 3 frogs has 3 mouths, 6 eyes, and 12 legs. You might be starting to notice a pattern here. So I'm going to be asking you to continue this pattern for all sorts of these frogs over here. I'll be waiting. Found a pattern? Okay, let's see. If we have 10 frogs, how many mouths are we going to have, and how many eyes and legs? According to the pattern that you found, there's going to be 10 mouths, 20 eyes, and 40 legs. Then there's 100 frogs. We're going to have 100 mouths, 200 eyes, and 400 legs. So it keeps going on. And now we're asking, pretend that A is a number, okay? Pretend A is a number. And we have A frogs. We have the amount of A frogs. How many mouths are we going to have? How many eyes? And how many legs? And present it in the terms of A. As you can see here, we know that if we have 10 frogs, we're going to have the same amount of mouths because each frog has 1 mouth. So we're going to have A mouths. We're going to have 2 A eyes because each frog has 2 eyes, and 2A means 2 times A. So 2 A eyes. And we're going to have 4 legs because each frog has 4 legs, and we have A number of frogs. So that's 4 times A legs, 4 A legs. So now we're going to start using letters to indicate patterns. As shown in the picture, 4 matchsticks are required to build a square. 1. According to the method above, 2 squares require how many matches, and 3 squares require how many matches? So here's a visual of that. It continues on. So how many matches does 2 squares require? Well, this is 4, and then it adds on 3 more, so that's 7. And then 3 squares is going to add 3 more on from that 7 we already have. So that's going to be 10. And 2. How many matches does it take to make 7 such squares? So I'm going to pause here for a moment, and first, without learning anything yet, try to find the pattern. And then I'm going to ask you to express it with a variable. Okay, so go off and start thinking about what is the pattern here. And if I have the pattern, how many matches does it take to make 7 such squares? So as you might have gotten, it takes 22 whole matches to make 7 such squares. And if you had a pattern, and if it was correct, you should have gotten the same answer. It takes 22 matches to make 7 such squares. And 3. How much matchsticks are required to build 100 such squares? Well, the first square, we need 4 matches. So we come from first 0 matches and we add 4 more to make 2 matches, to make 2 squares. That's the second one. We're going to add 3 matches. And adding these on, we're going to know that the 100th square is also going to add 3 more matches from the 99th square, the square before. And from that, we can conclude how the pattern of how to find 100 such squares. First, we add a 4. That's going to be the amount of matches we already have for the first square because it's different from all the other ones. And then we're going to multiply a 3 to that square minus 1. So we're going to have 4 plus 3 times, in parentheses, 100 minus 1. And what it means is how many matchsticks that are required to build 100 such squares is going to be the amount of matches from the first square plus the amount of matches we're going to need for the rest of the figure. And if you're wondering why we need 100 minus 1, that's because this is already the first square, so we don't have to look at that. And after the 4, we really have 99 squares that adds 3 more matches. So it's going to be 100 minus 1. Or try to think it in a different solution and think, is there any other ways I could calculate this? Think about it. What is any other way that you can calculate this with? Got an answer? Okay, let's see. This way also works. We first put 1, and then we're going to add 3 more, keep going on. So the first square, we're going to have 3 matchsticks. But remember, we have to put 1 first. So we put 1 first, and then we add 3 more. 3 more for the second square, and 3 more. And at the 100th square, we're going to add 3 more matchsticks, just like all the other squares. So this way also works. We're first going to pretend that we don't have this one. So the first matchstick is gone. And then to figure that out, which is much easier, we can just multiply 3 by 100 because in that case, there are 100 unfinished squares put together. So that's 3 times 100 because in every of those 100 squares, there's 3 matchsticks. And then we have to put 1 first. So we add a 1 there. So that's 1 plus the product of 3 times 100. 4. If x is used to represent the number of squares, how many matches are needed to make x such squares? Well, we already have this, and it's asking us to make x such squares. Well, in the last problem, it was asking how many matches are needed to make 100 such squares. And now we're replacing the word 100 and the number 100 with x. So wouldn't that be the same pattern? Wouldn't that mean the same thing, except that it's not just 100 now, it works for any other amount? Think about that. Is that going to work if we just replace 100 with x? If we just pick a random number and replace that with 100. Turns out it does work because this is a formula or an expression or a pattern that applies to any number. Really, the expression is 4 plus 3 times the difference of a random number minus 1. That's all this equation means, except that in this case, our random number was 100. So we plugged 100 in, and then we got this equation for us to solve. So basically, it was the 100 had an x in its place at first, but then we decided to pick a random number or a random value for x, because over here you could also think of it as x. You could also think of it as x equals 100 in this case. So it would also work if we just put 4 plus 3 times the difference of x minus 1. So just like what we just talked about, we can replace this 100 with x. So the x square. And then we can replace this 100 as well. And if you think about it, if x did equal 100, this would work. So why not put in any value for x? After all, it is a variable. A variable is a symbol, in this case x, that has a value that changes. So the value is unknown. So let's see if we could first try to prove if this is correct. So let's say x equals 3. So that's going to be from the first square to the third square all the way over here. And then let's see it. So the equation is going to become 4 plus 3 times 3 minus 1. Remember, x equals 3 and we're taking that place. Then we simplify. So that's going to be 4 plus 3 times 2 equals 4 plus 6 equals 10. Is that correct? So this is 4, and then we're going to add a 3, so that's 7, and then we add a 3 again. That's going to be 10. So it does work. It is correct. It is extremely important when you come up with a pattern and you always want to kind of put a value in and see if it works, if it is correct, before you always answer that problem. So this works. And we can even do this the other formula too. So there's this way. 1 plus 3 times 100. This is going to become the x square, and the 100 is going to become x. So this is the same case. 1 plus 3 times x is going to give us the value of the x square. So now let's have an example. As shown in the picture, 4 matchsticks are required to build a square. According to a calculation method, to build 200 such squares requires blank matchsticks, and to build 2016 such squares requires blank matchsticks. So now pause the video, and I want you, and remember to actually pause it, and I want you to try to use one of the patterns or formulas that you just learned or you came up with. Whichever one that's correct, or whichever one that you would like to use. And then I want you to solve these blanks. And then after, unpause the video to check your answers. Ready for the answers? Great! So if we're going to use one of the formulas, say it's going to be 1 plus 3 times 200, because this is what x equals right now. X equals 200. We can simplify this, and then we're going to get 601 matchsticks. And we can use the same formula or the other formula for 2016, and then we're going to get 6,049 matchsticks. Now let's try something out. So as you can see, there's different figures over here. This is the first figure, second one, and third one. And it's asking, well, how many matchsticks are needed to create the first figure? This is the figure number, so there's the first, second, third, fourth, and so on. And that's the nth. This is asking for the second one, how much matchsticks are used to make this one? And the same goes for so on. Also, by the nth figure, I would like you to try to express that figure's matchsticks. I want you to make up an expression that's including this n in here. And remember, after you come up with it, always do not hesitate to put in one of these amounts, replace it as n, and test it out to see if it works. Unpause the video after. Got your formula? How much did you get? Here are the right answers. 7, 12, 17, and 22. And before I reveal the nth figure and its number of matches, stop and think about this. What is the relationship between the figure number and the number of matches? What is a relationship here? If you haven't noticed, the relationship is 5 times this figure number plus 2. For example, 5 times 1 is equal to 5, and then we plus that 2, which gives us 7. And then the same works for this. It's the same repeating pattern. 5 times 2 is equal to 10, and we add a 2 to that. That's going to give us 12. 5 times 3 is equal to 15. 17 equals 15 plus 2. And the same goes for 4. If we had put up with that pattern by now, we should know the nth one. Answer is 5n plus 2. 5 times whatever's up here plus 2. And that is a pattern. And as you can see, if we want to plug one of these numbers in, that would work. So now let's talk about it. Okay, talk about what we have learned. In the activity above, we use letters to describe the relationship between the number of squares and the number of matchsticks. Now think, can you give some examples of letters indicating the relationship between numbers and quantities? So think about something in everyday life that kind of has relationships between variables and the numbers and quantities. So when you were still in elementary school or primary school, you probably learned lots of formulas. Say you learned how to find the area of a rectangle. It was the width times the height. And that's exactly how we can use variables to represent them. Let's take a look at this table. For example, the arithmetic laws could have additive commutative law or the commutative law of addition. That was a plus b equals b plus a. Remember, the variables a and b can represent any quantity. And then the additive associative law or the associative law of addition was that the sum of a plus b plus c is always going to be equal to a plus the sum of b plus c. And then there's a commutative law of multiplication. That's ab equals ba. Remember when it's in algebra, because this is what we're talking about right now, algebra, you can always not write the multiplication sign. There's the associative law of multiplication, and that's going to be the product of AB times C is always going to be equal to A times the product of BC. Oh, and also right now I hope you're trying to memorize what you have learned before, because we're going to be using lots of the laws when we are going to be heading on deeper into this Unit 3. And then finally, the distributive property. And we have the sum of A plus B times C is equal to AC plus BC. You memorize them? Good, because we're going to be using them quite a lot during this unit. So, as I just mentioned, we can use variables to indicate areas. For example, if we want to get the area of a square, answer would be A squared. A squared, okay? Because it's the same value multiplying itself 2 times. So that's A squared. A times A, or A squared. And then there's, for the rectangle, AB. This is going to be the width and the length. AB, AB. And then for this, we have AH, because that's the height and the base. Then we have, for triangles, AH divided by 2. Finally, for the trapezoid, we have the sum of A plus B times H divided by 2. As you can see, these are all formulas that you have learned earlier on in your life, and we can literally use variables to represent almost all of them. Okay, so let's have another example. Jacob walks to school at a speed of v meters per second, and Addie rides a bicycle to school, and the speed is 3 times that of Jacob. Then the speed of Addie can be expressed as blank meters per second. We know that if Jacob walks to school at a speed of v meters per second, and Addie is 3 times the speed of Jacob, we can write it as 3 times v, or 3v. And then, as shown in the figure over here, the area of the shaded part in the figure with letters is, so we're asking for the area of this frame. Well, we know the height and the base length of each of these smaller rectangles. Then all we really have to do is first find the area of both of these, and then minus the area of the smaller rectangle from the larger rectangle. Well, we know that the area of a rectangle could be expressed as mn, because this is the dimensions that we're going to use to multiply them. And then this in the middle is going to be PQ. And so if we know the area of both of these rectangles, we can find the difference, which is going to be this. Remember, we never have to actually find one specific answer to all of these problems. All we have to do is find the expression from the formula. So the answers are 3v and mn minus pq. So the variable indicates the number. We have to memorize some tips. So for example, we can omit the multiplication sign when multiplying numbers and variables. When we're multiplying variables and variables, the number comes first when multiplying numbers and variables. For example, 100 times t. Okay, and the second one, it says that when multiple letters appear, the letters are arranged in the order of 26 letters. So nm we could write as n. And then the third one, when multiplying the same variable, it should be written in the form of a power. What this means is that, for example, if we have n times n, we don't write n because that would look weird. And so to keep it not weird and to kind of keep it more organized, we're going to write n to the second power. Fourth, when 1 or negative 1 is being multiplied by a variable, 1 is usually omitted and not written. So basically, if we have 1 times n, we could just write n because the 1 wouldn't really change anything. And for the negative 1, negative n. Okay, and 5. When the division operation appears in the formula, it is generally written as a fraction. When a mixed number is multiplied by a variable, the mixed number is converted into an improper fraction. So what this means is that if we have, say, x divided by 2, we usually would not write it this way. Instead, we would write it as x over 2 because you see how that could sometimes help later on because you could simplify and all of that. It's easier to explain as we get more into this unit. And also, it says that when we have a mixed fraction, it is usually converted into an improper fraction. Say we have the very simple mixed number 1 and 1/2. Since we already know that we can omit the multiplication sign, it could kind of get confusing and we might think of it as, and then if we do that, it might disrupt some of the calculation we are doing. Or maybe we could think of it as 1 times 1/2, which is definitely not the case. So yeah, it's usually good to convert it into an improper fraction. So if we have n divided by 3, we can convert it into n over 3. And if we have 1 and 1/3 n, we can convert it into 4n thirds. Okay, now let's try to do it. Determine whether the following formulas are written as a standard manner. If they're not standard, please correct them. So pause the video and try to see if they are written in the standard manner as we just talked about. Okay, let's see. So the first one, x times y. We can omit the multiplication sign, and while we do that is we might confuse a multiplication sign as a variable, as x. So it's usually good to just write it as xy. And then we have a mixed number times ab. Well, we know that if we have a mixed number, usually in the standard manner, we would convert it into an improper fraction. So if we convert it into an improper fraction, it would be 17/6 times AB, or 17/6 AB. And then negative 1 times n, nope, we do not need that. Sure, the multiplication sign is already omitted, but we can just multiply them, and we know that it's going to become n's opposite number, or n's additive inverse, so it's going to just be negative n. And then x3, well, we don't really do that. We usually put the number part first. We put the coefficient part first. Remember, that's a good word, coefficient. So we put the coefficient first, and that's going to become 3x. And then the last one, m divided by 3. Not really standard, not really like how we usually do it. It's usually written in fraction form, which is going to be m over 3. So this could be xy, 17/6 AB, negative n, 3x, and m thirds, or m over 3. Okay, now let's do some practice in class. Fill in the blanks, and I want you guys to first do all these problems and then unpause the video to check your answers. All done with all of the blanks? Good. Let's start with the first one. And frogs have blank legs. Well, let's just think generally, okay? No broken legs or anything like that. If we have a perfectly healthy frog and all N of them are healthy, how many legs do they have? Usually you would think of 4 legs, maybe you think of the first 2 ones as arms, but in this we count them as legs. So that means that each frog has 4 legs. We have N frogs, so that's going to be 4 times N or 4N, 4 N legs. And then 2. There are A chickens and B rabbits in the same cage. So there are a total of blank heads and a total of blank feet. How many heads does one chicken have and one rabbit have? Well, if it was perfectly healthy and normal, it would be 1. So how we could first write it could be 1A plus 1B. But we know that we can omit that 1 because it's not going to change anything. So we can just write A plus B because there's that much animals and each animal only has 1 head. So that's going to be A plus B, total of heads. And then for feet, well, chickens have 2 feet and each rabbit has 4 paws. So that could be 2A plus 4B because we can first calculate the number of feet that chickens have and the number of feet that rabbits have. So that would be 2A plus 4B. Okay, and the fourth one. Luke in English has a total score of A and a total score of B in mathematics. So the average score of these 2 subjects is blank. Well, do you still remember how to calculate the average score of multiple amounts or the average amount of multiple amounts or values? So it's going to be the sum of all of those values together divided by the number of values that there is. So the values that we have right here is A and B. And then since there are 2 values, we divided by 2. So the average score is A plus B over 2. Okay, now next. Use chess pieces to form the following set of patterns. So what it's doing is that each of these red dots here are chess pieces, and you want to fill out this table down below. So pause the video and try to do it. Okay, let's see here. So let's just first write down what we know. We know that the first one is 3, the second one is 6, and the third one is 9. If we already have this right here, we could probably figure out what's going to happen next. So over here we know that this, we got plus 3, we got a plus 3 again, and it's probably going to happen again. That should be the pattern. So right now we predict that the 4 is going to be 12 and the 5 is going to be 15. Let's see. Yep, we were correct. 9 plus 3 is equal to 12, and 12 plus 3 is equal to 15. Look, another pattern that you could see is the pattern number is always going to be a factor of the number of chess pieces. This is always going to be 3 times the pattern number. So we know that the pattern number is 10 times a 3, 30. We know the pattern number is 100, so we times 3, which is 300. So on the nth pattern, we're going to need 3n. Okay, now we're going to use some matches to make triangles. So here's the table. Here are the number of triangles there are in each figure. And this is going to where we're going to be filling the number of matches to make them. So pause the video again and try it out on your own. Coming back, let's see. So the first one, we can see clearly that's 3. So as last time, let's put down what we know. That's 3, that's 5, that's 7, that's 9, that's 11. Now, do you see any patterns here? Because right now, I want you to pause the video. When I say pause, actually pause it. And I want to see if this has anything in common. And try to find a pattern just in any way you can. And try to look for a pattern between the number of triangles and the number of matches. What pattern did you get? One pattern there is, because there could be more, is that the number of matches is 1 plus the product of 2 times the number of triangles. So if there's 1 triangle, we need to times the 2 and plus 1 to get to 3. So goes for the rest of the triangles, 2, 3, 4, 5. Let's just pick a 3 and 7. This could be, we know our pattern, that's 3, that's 2 times 3 plus 1. Is that true? Yes. Here, that multiplies to be 6 plus 1 equals 7. So that worked. Now let's see how many matches is it going to build in triangles. Well, we already know the pattern, so it's definitely going to be easy for us to be able to put it in n form. It would be 2n plus 1. Because remember, in this case, n is going to be equal to the 3. It's going to be in the 3's position. So that's 2n plus 1. So now let's do a class summary. We learned how to use variables to indicate numbers, and then that splits up into 2 categories. We first learned about using variables to indicate formulas and using variables to indicate quantitative relationships and patterns. So that's our summary for today. Now let's do a skill summary or lesson summary. So we learned 3 very important skills that we're going to need for the rest of the unit and later on in life. The first skill we learned was that we understood the meaning of using letters to express numbers. The second skill that we learned was that letters can be used to express previously learned arithmetic and calculation formulas. That could be stuff like the distributive property or how to find the area of a triangle. Those are all arithmetic and calculation formulas. And then our last and final skill, letters can be used to express quantitative relationships and changing laws in some simple problems. So that's basically using our variables and being able to use them to create a expression that could express the quantitative relationships or value relationships in the changing values of some simple problems. So, I hope you learned something from here, and remember, if you didn't understand anything, you could always go back and rewatch that part. So, if you have any more questions wasn't answered in this video, please feel free to add it in the comments down below. And I will see you next time for a lesson on polynomials. Remember to subscribe to 3 Inquisitive Kids and be await of our next lesson coming up. See you next time.